Swayam Prabha. Digital India. Educated India.
Dear students, so let's show you the strategies of electrochemical tuning again. Last class I taught you like Fenton's reagent, the new method. Let's come with all proper explanations and with proper data and the surface images. So mainly we will cover again the activities with some new treatment method and the with proper explanations. So you can search this all the classes these main keywords, so you may get more information like kind of research going on currently worldwide, like people also involved like tuning the effect of electrocatalytic effect with some different treatment. You also can think about who are doing your like future, who want for like PhD or higher study, please think about some new method. You please, that's why you should search in Google, like, or even if you search in all the slides you can see I already mentioned different references I already put. You please go through all the references, and please go also some more example of this study that is already reported by different group, so you please check it. See here, today I am going to show you some data like just before treatment and after the Fenton treatments. So I taught you this Fenton treatment can be done on gold electrode, gold disc electrode, that is solid surface like pure gold. Now I am going to show you this treatment also can be similarly can be applicable on nanoparticles also. So because you may think like bulk electrode and nanomaterial, how they are behaving, right? Because their activations not the similar, right? How they are behaving during the electrocatalytic activations or electrocatalytic treatment or effect, so that they all are not same, right? Bulk electrode has some on effect and nanomaterial has something else. So let's use this Fenton's reagent, that is EDTA, hydrogen peroxide and ferrous sulfate. This mixture when we apply for the gold nanoparticle, so what we can do, so we can modify this nanomaterial on some electrode. So suppose you have ITO, indium tin oxide electrode, indium tin oxide coated electrode. There you modified gold nanoparticle. How you modified gold nanoparticle on indium tin oxide? You can apply any gold nanoparticle modification method that I already taught you. You can use the electrodeposition method. Electrodeposition, like how you can deposit gold nanoparticle, I just summarizing. Like you can take your like your ITO electrode is there, and this is the electrochemical cell, electrochemical cell. Here you can use a gold salt solution, right? Which gold salt? Like chloroauric acid, HAUCl4, and here you can put one reference electrode and one counter electrode. So your working electrode should be connected with potentiostat, reference electrode and counter electrode they should connected with a potentiostat. Then you can apply some negative potential or maybe with some potential scan you can do. Then you can deposit the gold nanoparticle on the ITO electrode surface, or maybe you can synthesize chemically. Chemical synthesis you can follow like ascorbic acid reductions, or you can follow citrate method or sodium borehydride reductions method, and then those nanoparticle you can deposit on the ITO. On the ITO surface you can deposit all the nanoparticle that you are chemically synthesized. Now this you can take a petri dish, you know the petri dish, you can take a petri dish, there you can put all your small chip that is gold nanoparticle coated, right? Now drop your Fenton's reagent, right, up to this much. They should be fully dipped with the Fenton's reagent. Your Fenton's reagent contain ferrous sulfate, EDTA and hydrogen peroxide mixture that I taught you already in the last class, which chemical ratio you should follow. Then one important phenomenon you please remember, last time when I told you, when we use the gold disc electrode, after the Fenton treatment the surface become very smooth, right? The surface roughness, when you check the atomic force micrograph image, before treatment, after treatment, surface roughness changed actually. Before treatment is very rough. There you can remember the hill and valley type surface, but after Fenton treatment you saw surface become almost smooth. Here you can see when you did before treatment, this is the SEM image, scanning electron microscope image. You can see this all the gold nanoparticle on the surface, and after 90 minutes, means 1.5 hour, almost 1 hour 30 minutes, we treated with Fenton's reagent, and we show the number of nanoparticles and almost the similar. It means nanoparticle actually behaving different than gold disc electrode. Disc electrode case, surface almost it become knockout, surface hill and valley type surface actually becomes smoother. But nanomaterial case you can see something like similar. Then we checked actually the gold oxide, means is their number of nanoparticle is similar or not, if nanoparticle surface become changed or not. That also we checked gold oxide formation CV. See, before treatment and after treatment. See, this red one, this is the before treatment. Before treatment with Fenton's reagent. You see, this is the cyclic voltammeter oxidation peak and reduction peak. So by this we can actually measure, if we integrate this surface area, you can actually measure the surface actual your active surface area you can measure if you integrate this surface, this area. Now the oxidations or the reductions. You can see after treatment it is also almost similar, not much change. It means your actual surface area not changed much. Now come to the interesting phenomena that I am going to tell you. If you measure their electrocatalytic activity, so we checked hydrogen peroxide oxidation peak, or even you can try like some other substrates also like glucose or formic acid. You can see when treatment, no treatment, the hydrogen peroxide peak is something like this, but after 10-minute treatment or after 30-minute treatment, see peak actually shifted towards right. What is the meaning of this? If peak shifted towards right, it means your surface deactivated, right? It shifted towards right, more potential shifted. It means your surface deactivated. So although your nanomaterial coated your surface, your active area almost similar after treatment of Fenton for 10 minutes or half an hour, even we tried for the 1.5 hour treatment, but activity actually decreasing. It was not shown by gold disc electrode. In that case, your gold disc electrode case, what we have seen, surface becomes smoother and activity also decreases. But in this case, activity decreases but surface almost similar. But you can say, sir, because of aging also surface can be deactivated, can be changed, right? It can shift towards their right side, right? Because aging also can affect a phenomena. But after half an hour, this is also half an hour you are storing basically. Yes, we checked almost 24 hours we checked, there is not that much deactivation. Or even we checked almost 1 week also not that much deactivation. But Fenton treatment just for 10 minutes or half an hour is deactivated too fast. So this is kind of treatment. Like one treatment can deactivate the surface rapidly. So we check this one also for hydroquinone oxidation reductions. Not only hydrogen peroxide, we check the hydroquinone. You see, just no treatment when there was no Fenton. You see, this very oxidation peak and reduction peak, they are very close, right? They are almost, this is called almost reversible or semi-reversible, almost reversible this surface, because you can see the E hub value very close, they are very low because their oxidation P reduction is very close. So, they are very much reversible. But when you go for the treatment 3 hour, 24 hours, 72 hours, like we increase, now slowly we are increasing the time of the treatment. You see the peak shifted, see almost is quite shifted long, right? Here we see the oxidation speed after a longer incubations with Fenton's reagent. But if you see for aging in here, there also certain aging effects. So, almost 72 hours. So, almost 72 hours aging also can affect, because as I told, if you store for longer time, but aging can decrease the activations very slow, but Fenton's can decrease the activity rapidly, very fast. So, that you should remember. So, this decreased activity also we measure with the help of impedance spectroscopy, the EIS, electrochemical impedance spectroscopy. I think you remember last time I taught you, like if this is the x axis, we are measuring the impedance of real value, and y axis we are measuring the imaginary value. So, and you can remember, I think, right. So, like this impedance, this semicircle, this is the RCT, charge transfer resistance. So, based on this value we can measure the electron transfer rate. So, after the Fenton's treatment, you can measure the electron transfer rate also on the gold electrode surface. So, you have the gold nanoparticle on the surface, just gold just after the synthesis, and you can then immediately you can measure the electron transfer rate on the surface after the Fenton treatment. You wash the surface, then again measure the electron transfer rate, RCT value. So, although there is no protein molecules on the surface, still you may get the decrease of the RCT value. Means RCT value will increase, it means decrease of the electron transfer rate. So, if RCT value increase means electron transfer rate decrease. If see no treatment, very small RCT, this much, then 3 hour, 8 hour, 24 hour we are increasing the treatment, see RCT value, see RCT value, how the RCT value increases. So, it means although you have the same nanomaterial, gold nanoparticle, but because of the Fenton treatment, your charge transfer resistance actually decreasing, right. So, this impedance value actually predicting and giving you this information to you. Now, see the reason, this is very obvious, we can explain it, why Fenton treatment for the gold disc electrode case something different and gold nanoparticles case is something different. Why? This is because the gold surface, it has the very active site, right. So, mechanically when we polish the gold electrode, it has some active site of gold. So, that active site of gold can be dissolved during the hydroxyl radical attack. So, this hydroxyl radical can attack on the gold active site, especially the disc electrode case, it can be dissolved easily. That is why you are getting the smoother surface. Okay. So, during the Fenton treatment, your gold surface atom which is dissolved in the hydroxyl attack for disc electrode, that dissolution is not effective for the gold nanoparticle case, because this is very stable surface atom. Gold nanoparticle surface atom is very stable. This hydroxyl radical attack cannot be very much effective to dissolve that surface. That is why if you go back, the nanoparticle is same image, you see almost the similar, and you are getting this oxidation reduction peak of CB almost similar, because it is not dissolving. But disc electrode case, before it was like this surface, and after hydroxyl radical attack you can see the surface become almost smooth. So, nanoparticle surface actually is very stable, that is why. This is one probable reason. So, of course, the hydroxyl radical actually is not dissolving, and electrodeposited gold has the very stable atom surface. So, very active gold atoms are dissolved during the oxidations for the case of gold disc electrode. Okay. Now, the similar Fenton treatment I want to correlate with another treatment. See, in this slide I want to teach you again similar kind of Fenton treatment, but this is ultrasonic treatment. See, another interesting treatment come now. you know, generally after polishing of the gold electrode surface, I mentioned, like if you have the gold disc electrode, then we are polishing first the gold disc electrode with aluminum slurry, then we washing with DI water, then we are taking this gold disc electrode in a water bath. Then we are sonicating, right? Sonication, ultrasonication. We are sonicating this surface in a bath sonicator. We are using a bath sonicator. Then we are sonicating it for 15 minutes. But sometimes you may go for the quite longer sonications. But that effect now I am going to tell you. So if you go for a quite longer sonication sometime, it may impact on your gold electrocatalytic activity. How? So you may ask why you are showing there is a correlation with phantons. Yes, there is a relation with phantons reagent, and if you go for the longer ultrasonic treatment for this gold electrode surface just after polishing, after this mechanical polishing. See, here I am showing some cyclic voltammogram of the hydroquinone benzoquinone couple. Here actually I started from right side this cyclic voltammogram. It means I started from benzoquinone. So it is the starting point. So if you start with the benzoquinone, because it is the already oxidized species, right? So you can remember like hydroquinone, you know the structure of the hydroquinone, right? This is the OH, this is hydroquinone, and this one benzoquinone, right? And they can reversibly they can transfer on each other. So if it release if it release the 2 electron, and if you give the 2 electron again, then it can be reduced back to again hydroquinone, and this is benzoquinone. So when you start with the benzoquinone, because it is already oxidized species, right? It is already oxidized, and hydroquinone it is the reduced form. So if it is already reduced form, you cannot further reduce if you start from the right side of this cyclic voltammogram. So if you start from the right side, then you have to use the benzoquinone. So first benzoquinone is first reduction. So this is the reduction scan, and then again oxidation, oxidation scan. But if you start from the hydroquinone, then you have to start first oxidation, right? Because it is already reduced form. So then you have to start from the left, then to right. First oxidations and then reduction. If you start from the hydroquinone. Okay, so that's the electrochemistry. Just I am reminding you basic time to time. I also remind you so that you can correlate with your data, with your basic concept. See, so we started the benzoquinone. So just after 0 minute means just after mechanical polishing. See, you can see the very high sharp of reduction peak and oxidation peak, and they are very close. It means your surface is highly electrocatalytically active. That's why. Now 1 hour, 2 hour, 3 hour, 4 hour means quite longer ultrasonications I am doing. Then you may face the deactivations of the sensor, your surface. So generally people are not doing the longer incubation, this with sonications. But if you go for this, what is the effect? Generally people are not check this effect also. You can see generally after 0 to 4 hours, if you store just in the water bath, if you take a water bath and store your gold disc electrode just in water after polishing, you can see in this calibration curve there is not that much electrocatalytic activity change. So current almost similar. But if you go for the sonication, see, is shifted, your oxidation peak shifted towards right, and reduction peak shifted towards left. It means electrocatalytic activity is decreasing, see, like this way. So with time your current also peak, current peak also they are also changing, and catalytic activity decreasing. So this means during the ultrasonication something going on. What is this? What is the factor? Let us try to learn. So first we investigated the surface roughness. As I told you in the phantom treatment, that before the phantom reagent treatment, the surface become very rough after the mechanical polish. You can see the surface roughness 13.8, and then after the sonications, when we sonicate sonication for like 1 hour. If you go for the 1 hour sonication, you see surface becomes smoother and roughness become 8.4. So, it was 13.8, now become 8.4 nanometer. So, it means that again the active surface again knock out and it become smoother and deactivated, right, deactivated surface. You can say if your surface is not polished, means your surface is not that much rough, then it is difficult to check the roughness change. So, at least your surface should have the hill and valley type rough surface, then only you can see the roughness change during this ultrasonication, this ultrasonic treatment. That is why we choose the surface after the mechanical polishing. The surface roughness becomes 13.8 nanometer and it become now 8.4 nanometer just after sonications. So, here is the whole images you see when your surface not polished, just before polish 1.7 nanometer, and in that case just sonications 1.6 nanometer, not that much change. And this is the surface just after polishing, this is the AFM atomic force micrograph images 13.8 nanometer, and then after sonications it become 8.4 nanometer. So, we can clearly see the changes. Now, so I will come the final conclusion why the electroactivity changes. Means step by steps I am coming, I am showing you like the changes happen. So, XPS, X-ray photoelectron spectroscopy also we can measure the surface. So, why we need the X-ray photoelectron spectroscopy? XPS can help you to measure the contaminations of your surface, means if there is any carbon contamination or not, if there is something else present or not. During the sonications, there is possibility of the surface contamination, maybe you can think, right, and it can block the active surface area, the surface contamination. That is why maybe you can get the deactivations. So, then that is why you have to prove the surface like contamination factor, like if there is any carbon present or not. See, let us come first the carbon based things. So, you can see the carbon peak around 285, this area you can see the carbon peak before sonication, after sonication almost similar. It means there is not that much carbon based contamination. So, we can eliminate easily the contamination effect for this deactivation. And we check the you can check the oxygen also, oxygen region. So, I mean if there is defined like organic material, it may carbon oxygen also may present, right. So, oxygen peak also you can check in this region. So, what is the XPS? That is why if you have to study the photoelectron spectroscopy, X-ray photoelectron spectroscopy, it will help you to measure different surface material if it is present, and easily you can predict the region of deactivations. And you can see this 84 and around and this region 88 something, you can see the gold peak. This region we can see the gold peak, sharp 2 peak you can see. So, if your surface cover, means if your gold surface is covered by some impurities, then definitely your gold peak also can be covered. You can see that also not that much, not means if it is too many, if it is contamination, then it should decrease like this up to here, but not, it was not happen. So, it means something else can decrease the activity. So, I am actually teaching you that sequentially and systematically you should understand how you should characterize the surface if you want to explain a factor for change of electrocatalytic activity. So, in this case also we can imagine that there is no contaminations. Now, let us come the correlation with the Fenton's reagent that I told you, no. So, Fenton reagent case, you know, like OH dot hydroxy radical actually generating. So, actually it is well known during the sonication there is a possibility of the hydroxyl radical generation, but that hydroxy radical that I taught you, that after mechanical polishing this hill and valley type this surface, it can attack and it will dissolve this surface roughness, and you will get the smoother surface, you will get the deactivated electrocatalytic activity can be deactivated, right. That phenomena is checked, it was examined by potassium iodide dosimetry. What is potassium iodide dosimetry? You can check before and after sonications. Before and after sonication, you can check if there is a hydroxy radical is generated or not. See here, potassium iodide solutions was used. So, during the sonication, then the iodide ion, that iodide ion can be oxidized during the hydroxy radical generations. So, iodide, it can form I3 minus, and this can be done, these oxidations can happen only because of this generation hydroxy radical. So, you can see here this UV visible spectroscopy. This is the UV visible spectroscopy diagram. You can see the before ultrasonic treatment and after the incubations, means we dipped in the potassium iodide solutions for the 1 hour, and also we dipped the electrode in potassium iodide solutions during the ultrasonic treatment. Then we can see this peak. This peak we can see only during the ultrasonic treatment, but not just during the simple incubation with the potassium iodide. So, what is the meaning of this? So, this means oxidation iodide that was negligible, means that is almost not done, not here during the 1 hour incubation without ultrasonic treatment, but this peak you can see around 355 nanometer. This is because of conversions of the iodide to I3 minus, and that because of the hydroxyl radical. So, these experiments actually prove that hydroxyl radical is generated during the ultrasonic treatment. Okay. So, we are concluding this, that phantom treatments and ultrasonic treatment, there is a correlation, right. So, phantom treatment, this is a very simple treatment. Ultrasonic treatment means this is a very simple, like you can like just take a water bath and then dip your electrodes and then sonicate it for quite some time. Then you, by this way you can deactivate the surface. And what is the reason for this deactivation? That you can correlate with the Fenton's reagent. And there is also possibility of the hydroxyl radical generations, and that hydroxyl radical can smooth your gold electrode surface and activity can be changed. So, this is the correlations of these two treatment. So, today also I taught you like some another treatment, that is the ultrasonic treatment. Again in the next class I will cover some another tuning method, then I will correlate all the treatment method and I will explain one by one the reason of the deactivations. Okay, thank you.